Okay, so thanks to Sarah and the two Seans for continuing to organise this series and for inviting me today. So I would like to, I'd like to talk about some work that I did earlier this summer, finished earlier this summer, which is about solving polynomial equations in primes. Now, the most general form of the question would be this: how many solutions are there to f of p1 up to pk equals n? Where here f is going to be some polynomial in k variables, and maybe n is fixed and you want to count the number of solutions to this equation in primes either full stop or inside some box or something. So here f is a fixed polynomial, think of the number n as fixed, and we want to count solutions in primes. In general, more variables makes for an easier problem. Higher degree of f makes for a harder problem. So the simplest case is when f is linear, and there we've been able to handle as few as 3 variables for about 100 years. So we can count solutions to p1 plus p2 plus p3 equals n, when n is odd at least, and this is the Ternary-Goldbach problem. So this was solved in 1937 for large n by Vinogradov using techniques of Hardy-Littlewood, and famously Helfgott in 2013 finished this off completely, addressing all values of n down to 5. And that's about as far as we hope to go anytime soon in the linear case. The binary problem is essentially the Goldbach problem, still seems totally out of reach. So the next degree up from linear is quadratic, of course. So what about when f is a quadratic form Q? Well, if that quadratic form is diagonal, then methods of Weil, which are very closely related to those methods of Vinogradov and Hardy and Littlewood that I just mentioned, they will allow you to count solutions to a form in 5 variables. So for example, if you want to know the number of ways of writing n as a sum of 5 squares of primes, that is something that you can do asymptotically, at least if n satisfies certain local conditions. Now, reducing this to 4 variables is a pretty notorious open question. Maybe not quite as notorious as Goldbach or twin primes, but amongst experts, this is still a well-known open question. Which numbers are the sum of 4 squares of primes? And in particular, is it the case that all sufficiently large n that are congruent to 4 mod 24, which is a sort of natural necessary condition, are the sum of 4 squares of primes? So that's an unsolved problem. Now, this was about diagonal forms. If I look at general quadratic forms where you allow off diagonal terms, then things get a lot harder. And the state of the art until this work that I'm about to tell you about was this result of Lilu Zhao from 2016. And he was able to count solutions to quadratic forms in 9 prime variables, at least if the form is non-degenerate. So if it's secretly a form in 7 or fewer, 8 variables, but you've just sort of added a dummy 9th variable, obviously you can't expect to handle that. So for non-degenerate Q, he could count solutions. All of these papers that I've mentioned use the Hardy-Littlewood circle method in some form. And all of them, so the Ternary-Goldbach for linear equations, Hua's result on diagonal quadratics in 5 variables, and Zhao's result on general quadratics in 9 variables, they are all at the limit of what the Hardy-Littlewood circle method can do for you without additional ideas. I'll be talking a little bit more about what I mean by that in the case of off-diagonal quadratic forms a bit later on.
Ben, I mean, you're talking about positive definite forms or not necessarily?
Not necessarily. So if your form is positive definite, then you naturally expect just finitely many solutions in primes, and then we can talk about an asymptotic for the total number of solutions. But if the form is indefinite, well, then you're going to expect infinitely many solutions unless there's a congruence obstruction. But then we can talk about counting the number of solutions in which the primes take values up to x. So for example, primes in some box. So there's no assumption here on definiteness. So the main theorem I want to talk about today is a reduction of this 9 to 8. So counting the number of solutions to a quadratic form in 8 variables, subject to a fairly mild assumption on that quadratic form Q that I'll go into a few more details of later. So that's the main aim today. Now, before I begin stating things a bit more precisely, I just want to go over a little bit of notation, most of which is pretty standard and I expect known to most people attending the talk. Whenever we talk about primes in analytic number theory, it's natural to introduce the von Mongot function lambda, which is a weighted version of the characteristic function of the primes. So it's log p on prime powers. The proper prime powers of degree 2 and higher are very few and far between and usually can be discounted. And it's 0 otherwise. So kind of a weighted version of the primes. There's also a local version of this, which is a bit less standard, the mod q version of von Mongot. And this is a function on z mod qz, where q is any positive integer, which is supported on the numbers co-prime to q. So those are the residues that prime numbers are likely to take. And it's normalized so as to have average value 1. So that's the local von Mongot function. Now I'm going to be dealing with forms in many variables. And rather than writing things out explicitly, it's useful to introduce this sort of tensor power notation. So when I write lambda tensor 4 of x, what this means is that x is a 4 vector, x1, x2, x3, x4, and I'm taking the product of the von Mongot function over its entries. And similarly for other functions. And then finally, I'm going to be looking at quadratic forms on the integers in 8 variables. And it turns out to be rather more than convenient, important to split those variables into 2 groups of 4. So you split the 8 variables into 2 sets of 4, call them x and y. So x and y are then vectors of length 4. And then you can write a general quadratic form as x transpose ax plus x transpose by plus y transpose cy, where here A, B, and C are 4x4 matrices. You can assume that A and C are symmetric. So that's a fairly natural thing to do, it will turn out. And then finally, something quite non-standard, something that turns out to play an important role in what I'm going to talk about is this matrix delta. So delta is a 4x4 matrix, which when B is invertible is defined like this. So it's 4, B inverse A, B inverse transpose C minus the identity. And this is something that I hadn't seen before, but it bears more than a passing resemblance to the discriminant b squared minus 4ac of a quadratic form in 1 variable. So I think of it as a kind of matrix discriminant of the quadratic form. So that will come up quite a bit later. So let me try and state a more precise result. So quadratic forms in 8 prime variables. I think this will be something that's familiar to people who've looked at these kind of results, circle method type things before. If you haven't, it may seem a little bit technical, but I won't be relying on this in what is to follow. So suppose I have a quadratic form Q in 8 variables, and I'm going to impose a few conditions on it, which I call being generic. So the determinant of AB is not 0, where here A and B are those 4x4 matrices arising in the expression of Q. And that discriminant delta has 4 distinct eigenvalues, none of which are 0 or -1. Then this statement is that the number of prime solutions to that quadratic form equals n. So the expression here on the left is counting prime solutions to Q of x1 up to x4, y1 up to y4 equals n, weighted by the von Mongot function. That is given by the expression on the right, which has the form of a main term plus an error term. Now, the error term is the standard sort of error term that always comes up in analytic number theory. And the way to think of this is it beats the main term by an arbitrary power of a logarithm. And the main term is a product of a kind of local factor here and x to the 6, which is quite natural here because I'm summing over x to the 8 variables, but I'm imposing a quadratic condition on them. So I sort of expect around x to the 6 solutions to such an equation. Right, and what's that local factor? S of nx, it's a product of Archimedean data and p-adic data, which basically reflect how likely it is, first of all, that that quadratic form has a solution over the reals, of the positive reals, which it has to if it's going to have prime solutions. And secondly, whether there are any p-adic obstructions to that quadratic form having solutions in primes. So for example, I'm not going to be able to solve 2x1 squared plus up to 2x8 squared equals 1 for two adic reasons. So then the factor beta 2 then would be 0. Okay, so here again, you don't need to worry too much about this. This is a precise expression for this beta sub pn. It's kind of a p-adic density, and b sub infinity is reflecting the number of positive real solutions to this quadratic form being equal to n. So this beta sub infinity, for example, would be 0 if the quadratic form was negative definite and I tried to take n to be positive. So that's just a precise statement of the main theorem. But if you don't want to engage with the details, yes?
Oh, sorry, Ben.
Yeah.
Were the beta p's, are they going to be the same limit as if you didn't impose the congruence restriction? Sorry, the coprime condition, and you just weighted them with 1?
No. No. I mean, this definitely will have some effect here.
Okay.
So for example, you would see that. So in the case of sums of 4 prime squares, if you require the primes all to be odd, that's got to be 4 mod 24 automatically. And that would be reflected here in this singular series if I was looking at 4 variables instead of 8. Whereas, famously, if you're looking at all integers, everything is a sum of 4 squares.
Okay, but the singular integral is the same as the non-prime problem, right?
Yes, absolutely. Yeah. So
okay.
The singular integral here, this is what people in the circle method call the singular integral. This is just reflecting basically positive real solutions. So if there are no positive real solutions, you don't expect prime solutions. But you're right that this is the same expression that you would obtain if you were thinking about just solutions in all integers without the restriction of being prime. As I said, I'm not going to dwell on this anymore. If you want, you can just think of this as an expression for the number of prime solutions of this quadratic form being equal to n. And it comes with a main term that's the one that we expect in this kind of problem and is very similar to what comes up in other problems of this general type. The error term beats the main term by any power of a log that you like, and that's also exactly what we expect in problems of this general type. Okay. So there were some conditions. Let me just go to the chat. Oh, sorry.
I just said thank you.
My pleasure. My pleasure. There were some conditions mentioned in that theorem, and I'm going to say that the quadratic form is generic if it satisfies them. So the conditions were, just to remind you, if I split the quadratic form into 2 sets of 4 variables, so I write it as x transpose ax plus x transpose by plus y transpose cy, then I need to assume that the determinant of AB is not 0, and that discriminant that's defined like this is a 4 by 4 matrix, has 4 distinct eigenvalues, none of which is -1 or 0. Okay, so there's some slightly technical conditions, but the main point about this is that generic forms are Zariski dense in the space of all forms. So in other words, being not generic, so not satisfying these conditions, is an exceptional situation. It's a positive codimension set of quadratic forms. So any quadratic form that you write down at random is certainly going to be generic and therefore covered by the theorem. Okay. So now let me get into a few more details. Let me just check the time. So having said that the circle method doesn't suffice for this kind of problem, nonetheless, we start by using the circle method. So the first step in the circle method is to write the expression that we're interested in. This expression on the left here is a weighted count of prime solutions to quadratic form equals n. So we write it in terms of a Fourier integral. This is the expression on the right. So t here means just r modulo z. So it's the integral from 0 to 1. Where s is an exponential sum. So it's the sum of product of 8 von Mongolf functions twisted by e to the 2 pi I theta q of xy. So twisted by a quadratic phase. So that's now the verification that this formula at the top is correct is one line. This just follows immediately from the orthogonality relations for characters on the circle. Right, so that's the first step of the circle method. The second step of the circle method is usually to divide the set of thetas that we're looking at into 2 sets, those that are close to a rational with small denominator, and those are called the major arcs, capital M, and all of the others, which are called the minor arcs. And usually what happens is that the major arcs give the main term in any asymptotic formula that we're going to be getting. And the minor arcs give a smaller contribution. So they have the status of contribute just to an error term. And usually we can't hope to, usually we could evaluate the major arcs sort of fairly precisely, there are formulae for them. But with the minor arcs, we have to settle for just upper bounds. And we can't really hope to exploit any cancellation in signs between this s of theta and e to the minus 2 pi I theta n. And so the best that we're really going to be able to hope for is showing that the absolute value of s of theta, the exponential sum at minor arcs, is on average small. And that's going to be my general plan. So this is an entirely standard setup for the circle method. And what primes only enter into the treatment of the major arcs, and that is totally standard. I've just been informed that my internet connection is unstable. Am I still audible?
Now you are, but it was bad for a bit.
Oh, okay. So how much did you miss?
So your what you said came through, but it was a little like robotic sounding.
Oh, okay. Well, that might just be me. I'll start from the top of the slide. So, yeah. Let me just briefly go back. So I have a standard setup for the circle method. We're going to divide into major and minor arcs. And we need to show that the average of the exponential sum over the minor arcs is small. So we're thinking about primes, and the specific properties of the primes only really enter into the treatment of the major arcs. And that portion of the analysis is totally standard. And in fact, it can be done with far fewer than 8 variables. It can be done with 5 variables. And this is a standard thing that we can lift. I actually just lifted it pretty much straight from Zhao's paper, but it's standard in other places as well. And for the minor arcs, you don't use anything specific about the primes other than the fact that there are quite a lot of them. So by the prime number theorem, the number of primes less than x is about x over log x, which translates to this bound on the von Mongolf function. So the von Mongolf function is bounded pointwise by log x. And then the prime number theorem is that the average value of the von Mongolf function is 1. So all we need is this sort of pointwise bound and nothing else about the fact that we've got primes. So now I'm going to give a very, very abbreviated run through of the basic steps in the circle method, but I'm going to leave an awful lot to just, you have to trust me on this because this is sort of moderately standard and I want to go into the less standard parts. So by what I would call a fairy dissection argument, so dividing the circle into little intervals about rationals appropriately, you can actually reduce to the case where theta, the point on the circle that you're looking at, is actually a rational. So it's actually rational rather than just near a rational. But if we're interested in the minor arcs, it's going to be a rational whose denominator is not tiny, because otherwise it would be a major arc. So we reduce to actual rationals. So at those points, we've got an exponential sum. And by standard manipulations, that sum can be expressed in terms of sums that look like this sum t that I've written here. So these are sort of, what goes into this is various sort of averaging arguments, fairly routine things. But this exponential sum here is a nicer object than the s of theta that I had before. It's what we call a complete exponential sum. So it's a sum over the variables taking values in the whole of a group, z mod qz to the 4. So this is going to be a crucial definition in what follows. T of f1, f2, where here f1 and f2 are two functions on z mod qz to the 4. T of f1, f2 of r is this normalized average over x and y of f1 of x, f2 of y, e to the 2 pi I r q of xy, capital Q, over little q. So this is a kind of complete exponential sum, which you can use to evaluate the exponential sum s of theta that comes up in the circle method. So as I said, I won't say anything more about how that reduction goes. It's not immediate by any means, but it's a fairly standard thing. So there it is again, that exponential sum. So let me just recall f1 and f2 here are just functions on z mod qz to the 4. These are complete, which means that the variables range over a whole group rather than just an interval. And what I've got here is a character on that group. So this is a natural looking sort of object. So we're going to think of f1 and f2 as basically just bounded functions, pointwise bounded by 1. In the application to primes, to quadratic forms in 8 prime variables, they're basically going to come from the von Mongold function, at least sort of translated versions of the von Mongold function, but that's not going to be important in our subsequent treatment of them. So again, we're just going to forget that we have primes and we're just going to consider bounded functions from now on. Now, it turns out that if you could show the following bounds, if you could show that those exponential sums t were bounded by q to the minus delta for some positive delta, that would be enough to close the analysis and to get an asymptotic formula for quadratic forms in 8 prime variables. Okay, so that's what comes out of sort of quite a bit of fairly standard analysis. You want a bound like this. Now, why is that bound natural? And indeed, why have I put this q squared out the front there? Well, it turns out that there's a kind of trivial bound, although it's not totally trivial, for these exponential sums. And the trivial bound is that they're bounded above by 1. So whenever you have an exponential sum t like this, where f1 and f2 are one-bounded functions, that exponential sum is bounded by 1. And let me explain why that is. So the reason that is that you can think of that exponential sum as an inner product over z mod qz to the 4 of the function f1 with a certain operator applied to f2. And that operator is twist by a quadratic phase. So you twist by e to the r y transpose cy, I guess. Then you take a Fourier transform. So you multiply by e to the rx squared x transpose by. And I've normalized by this q squared here, because then my Fourier transform is unitary. And then I twist by another quadratic x e to the 2 pi I x squared ax over q. So this phi r is a unitary map on L2 of z mod qz to the 4 because it's a composition of 3 unitary maps. The composition of twisting by a quadratic phase, which is obviously unitary, then a unitary Fourier transform, and that's where this q squared is the appropriate normalizing factor to make the Fourier transform unitary, and then twisting by another quadratic. So it's a unitary operator. And once you see that, the trivial bound that I claimed on T is just a one-line application of Cauchy-Schwarz. So by Cauchy-Schwarz, that inner product of f1 with phi of f2 is bounded by the L2 norm of f1 times the L2 norm of phi of f2. But because phi is unitary, the L2 norm of phi of f2 is just the L2 norm of f2. And this is bounded by 1 because the functions are pointwise bounded. Moreover, this trivial bound is best possible in general because I could just take the function f1 to be, I could take f2 to be some function f, and then f1 to be phi of that function f. And what I'll get is then just phi of f inner product phi of f, which is the L2 norm of f, which could very well be just equal to 1. So we've got this trivial bound, and it's also sort of trivially the best possible bound. So let me summarize where this puts us. So I had stated, suppressing quite a lot of computations that it would have been sufficient for us to get this q to the minus delta bound on these exponential sums t for some positive delta. Unfortunately, we can't do that. All we can get is the trivial bound that those exponential sums are less than or equal to 1. And that's best possible in general. And this is, I think, what I would mean by saying that the circle method cannot handle quadratic forms in 8 prime variables, because you end up naturally led to needing to get a bound for certain exponential sums that's slightly better than the trivial bound, but there is no such bound. Okay, so the question then is, how do we make progress from here? Well, the first thing to do is to go back to the analysis that I didn't show you, because it was quite long and fairly standard, that it would have been enough to get this slight improvement on the trivial bound. And if you go back to that analysis and just be a bit more careful, it turns out actually that you don't need that bound pointwise for every r, but you just need an average version of that bound. So it's enough to show that those exponential sums t, we can't hope to show that they're always small, q to the minus delta, but we just need that on average over r. And the example I showed you to show that the trivial bound is sharp will only work for 1 r at a time. So there's hope of doing this. So a counterexample that shows the trivial bound is best possible for r equals 1 won't necessarily be a counterexample for r equals 2.
There's a question in the chat.
Yeah.
So what is special about 8 equals 2 times 4 here? I imagine the same bounds hold for any even number of variables.
Yes, but it's when you, so you're asking me a little bit to go inside parts of the circle method argument that I haven't told you about. So what you're going to have to do is sum that bound over all r modulo q and then sum over q. And when you've got forms in 8 variables, if you only use the trivial bound, that sum just fails to converge. And what would make it converge is a slightly better bound of q to the minus delta. When I've got forms in 10 variables, that sum will just converge. And so the trivial bound would actually be enough in that case. Great. Okay. So by being even a bit more careful, you can also restrict to q being square free and odd, which is super helpful later on, as we'll see. So the question then is, can I hope to prove this average estimate? And here is where the key idea of the paper comes in. So I was looking at these operators that involve taking a function f, twisting by a quadratic, taking a normalized Fourier, a unitarized Fourier transform, and then twisting by a quadratic again. So I had a specific example, phi r, but this is a general type of operator, and it's a unitary operator on L2 of z mod qz to the 4. And the key observation is that the set of operators of this general type, slightly enlarged, form a group under composition. I mean, of course they form a group under composition, but the point is they form a rather small and explicit group under composition, and that group is the symplectic group. So let me just talk a bit about the symplectic group. I prefer to be very, very hands-on with the symplectic group and just define it totally explicitly. So if I've got a ring, commutative ring R with 1, then the symplectic group SP8 is going to be the group consisting of all 8 by 8 block matrices G. So here, capital A, B, C, and D are 4 by 4 matrices, whose entries are in R and which satisfy these conditions that I've written here. So you could alternatively phrase this in terms of preserving a symplectic, an antisymmetric form, but you can also be totally explicit. So this is a group of 8 by 8 matrices called the symplectic group. And so these operators phi under composition basically have the structure of a symplectic group, but the right way to express that is in terms of what's called the Weil representation. So let me tell you what the Weil representation is. So let Q be square free and odd. Then there is a unitary representation called the Weil representation from the symplectic group, symplectic 8 of z mod qz, to the unitary operators on L2 of z mod qz to the 4. And then there's also this phase function, which is slightly less important, And the Weil representation does the following. So it acts in the following way on specific elements of the symplectic group. So this S of E here, this is a kind of diagonal element, a block diagonal element of the symplectic group. And that element acts by dilation on under the Weil representation. So it takes a function f of x, and takes it to f of E inverse of x, twisted by some factor which I want you to ignore. The Fourier transform, well, this particular matrix J, which is also a symplectic matrix, in fact, a very famous symplectic matrix, 0 minus I 0, that matrix acts via the unitarized Fourier transform, again, twisted by a unit complex number. And then finally, this lower triangular matrix here, so I0 Wi with W being symmetric, that acts under the Weil representation by twisting by a quadratic phase, again times this factor that I want you to ignore. So these three particular types of element in the symplectic group, in particular the last two, act via Fourier transforms and twisting by a quadratic phase. And so the existence of the Weil representation is what I mean by the fact that these operators, the twisting by a quadratic phase and taking Fourier transform, form a group that's the symplectic group. Now, the existence of this is sort of, I guess this would be in the category of well known to experts. It's certainly well known if Z mod QZ is replaced by the reals, but actually in that case, it's not quite true. You have to lift the symplectic group to what's called the metaplectic group. It's also fairly well known when Q is a prime, and then it is an actual representation like this one. When Q is composite and square free, I mean, it's kind of, as I say, known to experts, but I couldn't actually find a reference for it. So had to go and deduce this for myself, but that was relatively straightforward to do. In fact, you can deduce it from the existence of the mod P versions of it. So this is the Weil representation. Any questions on this before I go on? Because this is going to feature quite a bit. Okay. All right. So you may recall that I was interested in this specific unitary operator that came up in connection with my exponential sums that I was looking at that were related to my specific quadratic form Q, which is the object of my whole talk. So this is a particular composition of quadratic modulation, Fourier transform, quadratic modulation. And therefore it corresponds to an element of the symplectic 8 group, and we want to know what that element is. And you can do a calculation that's not very difficult to figure out exactly what that element is. It basically just involves multiplying together a few 8 by 8 matrices. And what you come out with is this. So that operator phi r corresponds under the Weil representation to this element of the symplectic group, which is written down here. So these A, B, and C, they're all 4 by 4 matrices. And so this is an 8 by 8 matrix G. And G to the brackets R means that I twist that G by what I call a dilate. So the dilate of a symplectic matrix A, B, C, D, you take the B and the C and you divide B by R and multiply C by R. So this is this operation of dilation actually gives you an action of Z mod QZ star by automorphism. So we're interested in this particular element and its dilates, the Weil representation at those elements. So with all that set up, we can rephrase what was our key task. So our key task was to estimate a certain average of exponential sums and show that it's slightly better than the trivial bound. And I can now phrase that in an equivalent way in terms of the Weil representation, which is as follows. So this is just the same statement to obtain a non-trivial bound for this average. And these objects here, F1 in a product row of G to the R F2, these are what are called matrix coefficients. So what I want to estimate is an average of matrix coefficients. for the Weil representation. And that's a task that I can look at in generality. So let me do that. So suppose I have a finite group G, a unitary representation psi of it, and a probability measure mu on that group. So I'll relate this back to the actual question that I'm interested in a moment. Then the general problem is to give a non-trivial upper bound for an average of absolute values of matrix coefficients. So if I've got unit vectors v1 and v2 in the representation space of G, I look at the matrix coefficient in a product v1 with psi of x v2. So that's a function of x in capital G, and then I average it over this probability measure mu. So in our specific setting, G is going to be the symplectic H group on Z mod QZ. Psi will be the Weil representation of that group into L2 of Z mod QZ to the 4. And mu is going to be the uniform measure on this particular set of elements, this particular matrix G that I showed you before, that's associated to my quadratic form Q and its dilate. And v1 and v2 are the one-bounded functions f1 and f2 that occur in the definition of the exponential sum that I'm looking at. So that's the general setup, and that's how it's going to be applied in our specific case. In everything I'm going to say from now on, I'm going to assume that Q, which is a square free number, is actually prime. It makes the exposition a lot simpler whilst having most of the key ideas. And I'm also going to always assume that the underlying quadratic form Q is generic, although I won't get to saying exactly where the various assumptions come in. So this is a general problem. Estimate an average of matrix coefficients. And here's a general-ish strategy for attacking that problem. So the first step, I'm going to go over each of the steps of this strategy in a bit more detail after this slide. So the first step is, it turns out that you want to average these matrix coefficients over the probability measure mu. It's actually enough to average them over some high convolution power of mu, or more accurately, over what's called a symmetrized convolution power. So I basically just convolve mu together a load of times with mu opposite, which is the measure that is mu of x inverse. Okay, so that it turns out that if you can bound this, say with m equals 100, then you can bound the original average of matrix coefficients. So then you need to understand those high convolution powers. And what one can then hope to show is that those convolution powers converge to something. And actually, in many situations, including ours, they're going to converge to the uniform measure on a group H. And in fact, that group H is going to be the one that's generated by the support of the original probability measure. So that then puts you in what's pretty much a totally algebraic setting. I've got a uniform measure mu H on a subgroup H of G, and I want to average some matrix coefficients over that group. So it's almost pure algebra, and that's something that I can attack using representation theory. So what comes out of the representation theory is that such an integral is bounded above by basically, well, 1 over the square root of d, where d is the smallest irreducible, the dimension of the smallest irreducible subrepresentation of psi restricted to H. So the final task then is to show that that d is quite big. So if you can show that there are no small dimensional representations in psi restricted to H, then you get a non-trivial bound and you're finished. So that's the overall strategy. And what I'm going to do now is just talk over each of those 4 points, some at greater length than others, in the specific case that I'm interested in.
Ben,
yeah.
So this D refers to complex representation, right? So there's nothing to do with the H from the symplectic group.
No, indeed. So these are complex. All representations are unitary representations over C. Exactly. So the the Weil representation of SPH is a complex representation of dimension Q to the 4.
Right, thank you.
So this D, whatever D is, it will be a summand of Q to the 4, but you might have restricted to H, it might very well split into subrepresentation. In fact, the Weil representation, as I stated, it is not irreducible. It splits into 2 subrepresentations. Okay, so let me go in a little bit more detail into those individual steps. So the first step was this idea that it's enough to look at high convolution powers. So that's the easiest thing to do. It's really just a few applications of Cauchy-Schwarz that I won't give you. I think this is pretty much standard. I got the idea from a paper of Bourgain. I've seen Schradoff use this idea before as well. It's a sort of 3-line application of Cauchy-Schwarz to first relate the average over mu to an average over mu squared and then just iterate. So that I think is sort of fairly well known. So step 2 is to look at how these high convolution powers behave and show that they get close to the uniform measure on a group. And in fact, on the group generated by the support of mu, or more accurately, by these elements. So mu is supported on the elements g to the brackets r, so the dilates of this one fixed element g, and I need to look at the inverse is g to the minus r times g to the s, as r and s range over all of z mod qz. So the argument that I use to do this is, I guess you could say it's inspired by model theory, but it's really inspired by a blog post of Tao, where he had read a model theoretic version of his own algebraic regularity lemma. So it's a paper of Pillai, I believe, possibly Pillai and Stoychenko. But anyway, what one does is one uses the Langevin estimates, so counting points on varieties over FP, to show that as you do these successive convolution powers, they become successively flatter and flatter. So their L2 norms decrease at each step, and not just decrease by a tiny amount, but by a sort of quantized amount. That's what the Langevin estimates do. So they either tell you that, well, you get a sort of dichotomy. Either your L2 norm doesn't decrease very much at all, or it decreases by quite a lot. So then finish off with an argument from additive combinatorics. So you've got these convolution powers that get flatter and flatter and flatter, and that must stabilize at some point. And then you end up with a measure mu such that mu star mu is very, very close to mu in L2 norm. And that is a situation that additive combinatorialists know well. And it basically goes back to Freiman or Fournier, I think Fournier technically, that such measures have got to be very close to uniform measures on a group. So all of this argument is slightly abstract and doesn't actually explicitly identify H. So H is pulled out as an abstract group from this additive combinatorics argument at the end, which is ultimately this sort of Freiman type statement that a set with doubling 1.1 in a non-abelian group is close to a subgroup. So that's where the group comes from. So that's the sort of general flavor of the argument. There is a completely alternative way that you could approach this, which I'm pretty sure does work, which is if you're familiar with the whole sort of Bourgain-Gambard machinery that was further developed by Varju and others, that sort of machinery could also be applied here. So to try and understand repeated convolutions of measures. But the thing is that our measure is actually very algebraically defined. It's the dependence on this parameter R is sort of quite algebraic, and that lets you use some slightly cheaper arguments. Okay, so steps 3 and 4. So at this point, you've got down to estimating an average of absolute values of matrix coefficients over a subgroup H. If you use the Cauchy-Schwarz inequality, you can bound this above by the same average with a squared here. And that is something which has a formula. It's basically a form of Scher's lemma. Tells you that this is actually, if rho is irreducible, this is actually equal to the L1 norm of F times the L1, the L2 norm of F1 times the L2 norm of F2 divided by the square root, divided by the dimension of rho. And in the general case, you can split into irreducibles and get a similar bound. So this is just one application of Cauchy-Schwarz followed by a standard representation theory fact, that this average is bounded in terms of the dimension of the smallest irreducible subrepresentation of rho. So remember here that rho is the Weil representation on the symplectic 8 group, and H is some subgroup of that symplectic 8 group that at the moment we don't know explicitly what it is. We just know that it's the group generated by some matrices that we wrote down. Right, so step 4 is going to be hopefully that dimension is large, and that's where we get our non-trivial bound from. Okay. So how can we make use of this strategy? Well, we're going to, I think, we're pretty much forced to identify what this H is. So H, we want to say something at least about how the Weil representation restricts to H. And I think that means we need to know what H is. So in other words, we need to explicitly identify what the subgroup generated by these explicitly given elements is. And then once we've done that, we then have an algebra problem or a representation theory problem of understanding how the Weil representation on the symplectic group restricts to H. Now, when I was thinking about this whole problem, so here's the problem more explicitly. Right, so just to remind you, G is this particular 8 by 8 symplectic matrix that comes from our quadratic form Q. We then dilate it in this symplectic fashion, so symplectic dilate, and that gives us phi of Q points. And then we're looking at all of those phi of Q points times their inverses, and the group generated by that is H. Right, so when I was thinking about this problem, I just assumed that this group H would be the whole of the symplectic group. It seems like you've done enough sort of non-abelian stuff here, all these different dilates, that it should be expected to generate the whole group. And I checked that in the, there's a sort of, we're thinking about the symplectic 8 group, but you could look at a model problem in the symplectic 2 group. And I checked that, and indeed, H was the whole group. But the surprising fact is that that's not the case here. So it turns out that this H is not all of the symplectic group. The symplectic group has size about p to the 36, and this H is actually a group of size about p to the power 12. And what it is it's a conjugate of SL2 of FP adjoin this matrix discriminant. So this is, it's a conjugate by an element Tor. This is a particular element of the general linear group GL8 of Q. This SL2 of FP adjoin the discriminant is not actually a subgroup of the symplectic group. So you have to conjugate it to get inside the symplectic group. So that's a group of size p to the 12. Well, as I say, the whole symplectic group has size p to the 36. So if I have a little bit of time at the end, I'll explain why it is that all of the elements lie in that group. That required quite a lot of sort of ad hoc computations to realize that fact. Of course, just because all those elements lie in this group doesn't mean they generate, but it turns out that they do generate. And there are various tools that let you prove that things generate SL2. And in fact, for this kind of argument, the fact that we're in a subgroup that's got SL2s rather than SP8s is super helpful, because we can classify the maximal proper subgroups of SL2 rather easily, whereas the classification of maximal proper subgroups of SP8, whilst it's known, is kind of a pretty horrendous thing to try and get to grips with. So we can hope to show that these elements generate the group by showing that they don't lie in any maximal proper subgroup, because we can classify what those maximal proper subgroups are and just do a computation. So it does require a non-trivial amount of group theory. I mean, what's going to happen is this FP adjoin delta, at least if delta has distinct eigenvalues, it's going to be a product of fields. And so that SL2 of that ring will be a product of SL2s of fields. And so you need to use sort of the theory of subgroups of products of groups, things like Gorsaz's lemma. But it's all stuff that's well known and somewhat standard in the discussion of sort of convolutions of measures on groups. Right, so the final thing you need to do, so you now have that explicit group H, and you need to understand how the Weil representation restricts to H. So in principle, this is a purely representation theoretic problem, which you could in principle try and address with character theory, but that does seem like it just seems like a really unappetizing task. So you'd have to compute the character of the Weil representation and sort of figure out the restriction. And it turns out that there's actually an ad hoc technique that works just as well. So as I say, the Weil representation restricts to some representation of this group H, and so it decomposes into some irreducibles, and we want all of those to have dimension at least D, where D is somewhat large. And the property that's going to be useful is that this group H, which is a conjugate of SL2 of a ring, is what's called a quasi-random group. So that's terminology introduced by Tim Gowers. And that means that its representations are either trivial or have large degree automatically. So SL2 of FP is the classic example of such a group. It has the trivial representation, and then all other representations have degree at least P minus 1 over 2. So our H has that property as well, basically because it's just a product of SL2s. And so all we need to do is rule out a copy of the trivial representation. So in other words, I just need to show that there isn't any function in L2 of FP to the 4 other than the 0 function, which is fixed by everything in this subgroup H under the Weil representation. So once one realizes that this is the task, it's very unlikely that there could be such a function. It would have to have all sorts of invariances, and indeed fairly ad hoc arguments let you rule out the existence. So that can be done without too much difficulty in an ad hoc way. Okay, so just in the last couple of minutes, I want to just briefly explain where this group H comes from. So this is the key observation. So why are those, let me just go back to the task. So this is the task. So G is some symplectic matrix here, and I want to look at the group generated by all the G to the minus R's, G to the S's, where this means the dilates. So why are those restricted to a subgroup? And the reason is that you can do a kind of block, what I call block DUL factorization of an arbitrary element of the symplectic group. So you can write it as diagonal times upper triangular times lower triangular. So that always exists, and you can just compute what the A, B's, and C's are quite explicitly. And it turns out that the product of B and C is this discriminant delta. So why is that an interesting thing to do? Well, under this symplectic dilation, the diagonal term is invariant. These terms change, but the diagonal term is invariant. And so what that means is that when you do the dilation and take an inverse, the diagonal terms disappear, and you've only got those upper and lower triangular terms. And then you can just show by hand that those all lie in a conjugate of SL2 of FP adjoint delta. Okay, so once you see it, I mean, this took an awful lot of ad hoc by hand computations to figure this out, but once you see it, it's actually an easy check. Okay, so I think I will stop there. Thank you very much for listening.